I'm AJ Piergiovanni, and I'm going to present our work on evolving losses for unsupervised video representation learning. Learning video representations relies on large video data sets with hundreds of thousands of labeled examples. Obtaining this much training data is often very expensive. However, videos have many other forms of structure, such as the order frames occur in, and different modalities like audio that can be used to learn representations without any labels. Many previous works have studied different forms of self-supervised learning for video representation, such as predicting future frames, multi-modal alignment tasks, tasks translating from RGB to optical flow or other modalities, as well as determining if frames appear in the right order. However, there are many different combinations of these tasks, and each task has a different loss function with different possible values. What we wanted to study is how to best combine all these tasks to produce the best video representations. To do this, we formulate video representation learning as a multimodal multitask learning problem. For a given input video, we train a neural network to learn a representation that is optimized for all of these tasks. The goal is that this representation captures naturally different activities. In more detail, we train a network for each of the input modalities. Each network is then optimized for a set of tasks. The final loss function is the weighted sum of both the tasks and the distillations. We use distillation to infuse information from the optical flow and audio networks into the main RGB network so that the final network only has to use RGB input but is able to benefit from all the modalities during training. Since each task has a different loss function and different importance to the final representation, we use an evolutionary algorithm to find the optimal values for each one. Our initial population is randomly sampled from a uniform distribution and then trained on a set of random unlabeled YouTube videos. Once trained, we extract representations from the network and cluster them. We use these clusters to evaluate the fitness of this specific loss function, and we repeat this process until we find the optimal set of tasks for our goal task. For the goal tasks, we have two different methods. In the weakly supervised setting, we use some labeled data to evaluate the learned representations. Here, we apply our trained networks on a small set of labeled videos and then use the clusters as a classifier, and the accuracy becomes the fitness. In the unsupervised case, we are inspired by the idea that large datasets such as AVA and kinetics, the action classes generally follow a Zipf distribution. Based on this, we can measure the fitness of a certain loss function on how well the clusters match a Zipf distribution. The idea of distribution matching assumes we have this prior distribution which we assume the videos follow. Then for each loss function, we can obtain a clustering based on what the representation learned. We can then compare these clusterings to our prior distribution using KL divergence, and that can become its measure of fitness. We find that both the distribution matching as well as the weakly supervised clustering are extremely correlated, suggesting that this unsupervised distribution matching is a very good metric to evaluate video representations. To train our final loss function, we use a large set of 2 million 3-second clips from random videos taken from YouTube. We use no labels, data cleaning, or human verification of any type. This leads to both a more challenging and realistic evaluation setting of unsupervised video representation learning. We find that by doing this loss evolution, we are able to outperform ImageNet pre-training and come close to kinetics pre-training. We also find that while the weakly supervised and unsupervised losses both perform very similarly, taking some random loss function performs poorly, suggesting the evolution is an important component. Once we have this unsupervised representation, we want to determine how much more labeled data was needed to achieve good performance. We found that when using just 10% of kinetics, we were able to achieve quite reasonable performance. When using 50% of the data set, we were able to match training from scratch. When we used the entire data set, we were able to outperform random initialization. In conclusion, we presented an approach to unsupervised video representation learning. Our distribution matching is an effective way to evaluate representations without labeled data, and we showed the benefit of large-scale multimodal multitask unsupervised learning.